So we're going to continue to talk about phase transition. So like a general reminder, we talked about, we had a tutorial about the sudden pole approximation, and we said that we, next to the, from Landau theory, we have an approximation for the free energy. So next to the singularity point, so I'm going to call it F sin. We have the minimum of some function. So next to the phase transition point, we can approximate the free energy into something that looks like that, and then around this point we have some parameters of the systems like the magnetization and the specific heat that exhibit some like universal behavior, and then we talked about the critical exponents. So we have two kinds of critical exponents in a way. So we talked about four overall. So we have the exponents that relate to the magnetization. So for the transition, for the dependence on the temperature, we have the exponent beta. So this is for t smaller than 0. So it's like where so t is t minus t critical. So when the temperature is smaller than the critical temperature, so we are in the ordered phase. So this is the behavior of the order parameter. So this is where h equals 0, and we got it by minimizing the energy and looking at the first two terms. And the other exponent is where t equal to 0 and h is not equal to 0. So this is h to 1 over delta. And we got that by taking t equal to 0, so the first term go to 0, and then we have the first order with m and the odd order that relate to the magnetic field. So the second type of exponent relates to the divergence. So we had one is the specific heat. So the specific heat we get in general with the second derivative of the free energy with the temperature, and the exponent of the specific heat is minus alpha, and the susceptibility, which is the second derivative with the magnetic field, is t2 minus gamma. So those exponents describe the behavior of the order parameter, and those exponents describe the divergence of the transition. So, so because it's a second, second order phase transition, we have the divergence of the second derivative. So we have the second derivative with the temperature and the second derivative with the magnetic field, and those two diverges, remember from the figures that you're supposed to get from the simulation, that you have this divergence around the critical temperature. So you see this from both of those. Okay, so
Talia,
yeah.
For example, alpha equals 0, can we call it second order phase addition?
Not really, because you need to diverge at what t equal to what was more t equal to 0, so you need a critical point.
I mean, for example, alpha equals 0, but gamma is not.
Oh, so we have only the values of that.
Yes. Technically, it's also second order phase addition, or
like I cannot think about an actual example that follows that, because then you only have like it's like one-dimensional transition. Technically, I think you can define something like that, not for anything with magnetization. You just don't have such a system because you always look at the temperature. But I think you may have some phase transition in general that you can find that only depends on one parameter. So instead of because you always have phase diagram with like 2 parameters, so like first order phase transition, we always have like the volume and the temperature and pressure and stuff like that. So maybe you can have it with one parameter, but I'm not sure. Like I cannot think about anything, but I also cannot think about the reason why not. I need to think about that. Okay. But then also like this of course will be like yeah, no, I don't know. Okay, so we know the dependence with t and the dependence with h, but a question that came up in one of the earlier tutorials is what happens if I want to. So I have the two-dimensional space where I have t and h, and I know how to approach the critical point either from here or from here. But what if I want to approach the point from here? So I change both the temperature and the magnetic field simultaneously. So I'm not going to get either that or that, but something that depends on both parameters. So it's going to be a bit more complicated. So the derivation that you did or going to do, I think you already did video. So basically what we can do, we have the scaling hypothesis, which is the title of the tutorial, that say that we define a function that is a function of h over t to some delta, which is some exponent that we currently don't know. And we also have like t to some minus, let's call it y for now. So we assume that we can define such a function that is equal to the free energy as function of t and h. So instead of writing this function of 2 independent parameters, we have some relation between the way that the temperature change and the way the magnetic field change, and correspond to the free energy. So to talk about that, let's take a small step back and talk about homogeneous function. Okay, so let's assume in general we have some function of 2 parameters, x and y. So f of x and y is a homogeneous function if it follows. So if I take f of lambda x and lambda y, this is equal to lambda to the power n of f, x, and y. So specifically here, I have the same lambda for both parameters, so this is called like an homogeneous function, but that doesn't matter. In a more general way, I have lambda to the power a and lambda to the power b, so now it's not the same parameter. And this is equal to, let's say, lambda to the power c, f, x, and y. So if we have a function that follows this relation, what we can do is instead of write it as function of x and y, I can write it as function of a single parameter, because we see that we have a relation between the way that x change and the way that y change, because no matter which lambda we're going to choose, this is still going to work. So a, b, and c are some parameters that we don't know, so, because of course this is very general. So let's choose lambda in such a way that it's going to help us reduce the number of variables. So, for example, let's choose lambda to be y minus 1 over b. So now I can write f of x and y, and then instead of lambda to the power c, I have y minus c over b equal to f y minus a over b x, and this is just equal to 1. Right?
But you didn't reduce the y, you still have the y.
Yeah, I still have y. I'm not going to get rid of y, I'm just going to write the function in a different way. So now let's multiply both sides by that term. So f of x and y is equal to y minus c over b, f of y minus a over b, x, and 1. So
shouldn't it be y plus c over b? Y over plus c over b?
yeah. So the 1 is just so the 1 is just a number, so it doesn't change. So now basically I can rewrite that as y to the power c over b f of z. Let's do it like f tilde, where z equal to y minus a over b x. So we have we have a function of one variable in a way that like this is only dependent on z. We still had a dependence on y, it just given explicitly. So we just multiply all of the functions. So we don't lose information, we just wrote it in a different way. So why is that useful? So let's think about f as the free energy, obviously, and x and y, instead of x and y, we have the temperature and the magnetic field. So what Landau showed is that the free energy near the singularity, the phase transition point, is an homogeneous function, like only at that point, not for the value, but this is what we care about. So what it means is that this relation that we assumed earlier is basically true. So so in the lecture or also in the homework, you see that like so. I have a function of h over t to delta, and I can find delta by taking the two limits of t go to 0 or h go to 0, and then I can find like the specific scaling relation. So okay, so we now know that we can write the free energy in that way, and then I'll solve a question. I'm going to solve a question from a test, and in the question we're going to understand why is that useful for us instead of. Okay, so this is from 2015. Okay, so scaling relation of the free energy. So you have the Gibbs free energy of T and H equal to, put it in a very specific way, X minus H. So this is given in the question, so this is just a different way to write what you wrote here. So what you wrote here. So instead of lambda, we have x for some reason. And we have some general values for a, b, and c. We don't know what they are. And what the question asks us to do is to prove this scaling relation. So there's two scaling relations. This is one of them. The other one also includes alpha. And we need to prove that just by using that very general assumption. So what do we need to do? We need to find each one of them in the way that, in the way that we usually do, through that, and then see if it works. So let's start with beta. So beta is the exponent of the order parameter. So this is with the temperature. And we know that the magnetization, we can write the magnetization as a derivative of the free energy with the magnetic field, and then we take either the magnetic field to be 0 or T to be 0, because we don't know. So we don't know the general function G, but we do know the behavior for either on that axis or on that axis, either when T equal to 0 or when H equal to 0. So for beta, we need to take H equal to 0. Okay. So we don't have G explicitly, but we have the scaling of G. So what we do is like just the derivative by part. So instead of take the derivative of H, we say, okay, let's take the derivative of X, the derivative of G of XAT, XB, H with respect to XB, H instead of over H with X minus C, multiply by the derivative of XBH over DH. So this is just derivative of parts, you know. So this is going to give us XB minus C So this doesn't look very useful because we just wrote it as function of different parameters. But what we wrote here is basically the magnetization, but instead of, so if that magnetization is function of T, this magnetization is function of XAT and XBH. so now we have a scaling relation instead of for G for the magnetization. And what we're going to do is the trick that we did when we talked about homogeneous function, which is scale out one of the parameters. So, okay, eventually we want to take h to be 0. So let's choose x to be t minus 1 over a. And you will see in a second why. And then all of that, okay, write it here. So we get t c minus b over a and 1 t minus b over a h. And now we still need to take h equals 0. So this is equal to t c minus b over a m of 1 and 0. Because no matter what I multiply, this is a function of t, but I multiply with some things that go to 0, so everything here is 0. So what we eventually left with is the magnetization for 1 and 0. So this is just a number. It doesn't scale with anything. Just a constant. And we have dependence on the temperature that scales like t to some power t to some power that depends on a, b, and c. So this is t to beta. So we got that beta equal to c minus b over a. So let's write it here, just so we have it for later. Questions so far? Okay. So now we need to do the same thing to find delta. So for delta we have the exponent of the magnetic field. So we need to do similar derivation, but take now t equals 0. So let's erase just the last part. So the derivative is the same derivative because we still take the derivative over the magnetic field. So this is b minus c. So now instead of the scaling that we did before, we want to get rid of the expression that depends on age. So we choose x to be h minus 1 over b. And this is going to give us h c minus b over b and of h minus a over b t and 1. And now we take t equals 0. So this is m of 0 and 1, which is again just a constant. So overall, all of that is proportional to h c minus b over b. So this is h1 over delta, and then delta is b c minus b. Okay, so if you have questions, that's the time to ask, because we don't have a lot to do today. So the last exponent that we need to find is gamma. So this is the exponent that relates to the susceptibility. So the susceptibility is the derivative, the second derivative of the free energy with the magnetic field. So now
it's no longer equal to the magnetization, or it is
yeah.
still.
So the only difference is now we're going to take the second derivative, which means you need to do the derivative by parts twice. So we still have x minus c outside of the derivative, and then the second derivative of g with x a t and x b h with x b h, and then the second derivative of x b h will h.
Isn't it zero?
Hmm?
Isn't it zero?
What's zero?
The derivative of x to the ph over h, the second derivative. Because the first derivative.
No, okay. It shouldn't be. It's not the second derivative because it should be there. Because I do once derivative by parts, so I take one. This is the coefficient that counts of the derivative, and then I do it again, and it's also counts of the derivative. Yeah. So this is going to give us x to 2b. This is going to give us, this is basically the susceptibility again, that is a function of x a t and x b h. And I'm sorry that my x and my chi look the same, but I don't know how to do chi. So this is equal to x 2b minus c where t equal to 0. So now we need to choose the scaling. So because we want to take letter t equal to 0, so let's get rid of the magnetic field term. So x is equal to h minus 1 over b. So this is equal to, wait, yeah, sorry. This is h equal to 0. So we choose, yeah, we want to scale out the dependence on t, so we get an exponent with t. So x equal to t1 minus a, 1 over a. So this is equal to t, c minus 2b over a, 0, so this cancel out. So overall, this is proportional to t, c minus 2v over a, which means that gamma is equal to 2v minus c over a, and those are the three exponents that we needed. So now the only thing that's left to do is to put those in this equation and see if it works. So, so gamma, we said it's 2b minus c over a, and is that going to be equal to c minus b over a, and then delta minus 1 is b c minus b, and then minus 1 minus c plus b, so this cancels that, and then we have 2b minus c over a, so it works. Okay, so this is basically kind of the only question that someone can ask in that subject. The only change I think that you can do is give the other scaling relation, and you know, it's basically the same concept.
You said that there are only two scaling relations. You said that there are only two scaling relations. This is the first one, and
yeah, there's another one with alpha. So you either have gamma, beta, and delta, or alpha, beta, and delta. I didn't memorize the other one.
yeah, but in the last lecture we discussed hyperscaling, and
With video.
yes, and he mentioned that there are some other critical exponents like nu and mu.
Oh, okay, yeah. You
Probably,
have more.
yes.
Yeah, you have more critical exponents for like the correlation length and other stuff. But we just don't discuss about those in the tutorial. So we don't really have like anything specific to solve with that. So as far as it's come to like a technical question that we solve, we will focus on those. Okay, so this is basically the topic of scaling. So just, yeah. So I put, okay, there is a new homework about scaling. It's super easy. It's basically what we did here, but easier. So, you know. And there is another homework that is due to the end of the semester. And technically it's about something that they're going to teach you, I think, in like 2 weeks or something. So I wouldn't bother to try to do it now. But it's there if you feel like, I don't know, bored or something. So we don't want to just put it earlier. So those are basically the homework for the course. Okay, so I think that's it.
Yeah.